Well, good evening, everyone, and thank you ever so much for attending this evening. On behalf of the Institution of Mechanical Engineers and the Biomedical Engineering Division, I'd like to welcome you all for attending tonight's memorial lecture for our dear friend and colleague and past chair of the Biomedical Engineering Division, Dr. Patrick Finlay. I'm also pleased to welcome Sue here, his wife, this evening, and many of his family who are here and both online as well, I believe. So it's wonderful to have you all here, and thank you so much for attending. It is our great pleasure to welcome you here to the institution and to share with you some of our memories of Patrick and his passion for engineering in healthcare throughout this lecture event. Patrick was the first divisional chair that I was introduced to when I arrived at as a member of staff at the IMechE in May of 2013. I really had no idea what I was doing as a theme manager, and I had no real remit other than to produce a policy on topics related to engineering in society. At the time, a report was already underway, and I'd gone through, and it had gone through many iterations, and it had kind of become a little stalled with our policy team. So Patrick offered to step in and help corral the process. And it was at that point that I met him. I had a short meeting with him here at HQ to discuss how we were going to proceed. I was met with a very warm smile, two very blue eyes, and a very firm handshake. And I don't know, there was something about it. It was just like a little cheekiness that kind of tells you there was going to be a joke somewhere there, but it always never quite. We sat down to have a chat about this, and having explained to him that I knew absolutely nothing about biomedical engineering, he proceeded to very kindly lead me through a potted history of the subject and what he hoped to achieve as chair of the division, and ultimately what the report was about. It took several weeks of work. Rick and his colleague, Professor Anthony Bull, who's with us here this evening, to fully understand the context of the document. But after several more iterations, we agreed the final draft of the report, and the biomedical engineering advancing healthcare was finally put to bed. To knock on. The image that you see here is a snapshot from a video that Anthony, Patrick and I made to promote the launch of the report, and the recommendation that a chief biomedical engineer should be employed in every NHS hospital to oversee technology procurement and integration. This was quite a revelation for some and gave us an opportunity to speak at several occasions to the media about why biomedical engineering was so vitally important to society, and something that I am still continuing to campaign on today. Suffice to say, I went on with the help of Patrick and Anthony and many of the members of the Biomedical Engineering Division to start a new theme here at the institution in healthcare in 2015, as I recognised, as so many of us did, that engineering is already and will continue, engineering in healthcare is already, and will continue to play a fundamental role in everybody's futures. And of course, in the last couple of years, that has proven to be very accurate. My encounters with Patrick while often very short, were always very enlightening, very fun, and often somewhat cheeky. But not once did Patrick ever make me feel like I didn't understand the subject, or that he couldn't spare the time to explain some concept to me in a way that made me feel like I was part of the biomedical engineering family. Whilst I often feel like a cuckoo in the nest, this was never really the profession that I was trained in, I now find myself as chair of the Biomedical Engineering Division following in Patrick's footsteps. And I hope, and perhaps my committee members and colleagues will be kind enough to let me know if I'm doing as good a job as he did. During his time as chair, he had the foresight to recognise that bringing the biomedical engineering community together was going to be essential if we were to have any impact on policy and government. And so he put forward a case for changing the name of the division to an association, a place where everybody in the profession could be welcome. I'm not sure if Patrick saw the creation of the joint steering group. I believe he was aware of it, although he had not attended the biomedical committee meeting for some time at that point. But I know that he would be very pleased to see that we now have a flourishing community with 7 institutions and organisations now attending on a regular basis, bringing together a community of somewhere in the region of 200,000 people across engineering and healthcare. I personally feel that this really is Patrick's legacy, one that he would have been very proud to leave behind, an atmosphere and an environment that has enabled all of us to work together, including those of us who have only really just discovered the field. So now I will introduce this evening's lecture. Now I start my introduction with the word jugaad, and I apologise for the pronunciation of that. It was a word I read in a piece that had been written about Patrick, and I hadn't come across this word before, and it's actually a Hindi word, and it describes a flexible approach to problem solving using only the things one has to hand around you. And it requires real innovative thinking and the ability to adapt to your environment. In engineering terms, we kind of refer to this as distributed or local production or manufacturing, and it focuses on reducing costs, the sustainable use of materials, and creating socio-economic opportunities. To me, the word really does capture the spirit of what Patrick was and why he was so driven in his work, particularly in his field of robotics, where he wanted to see technology develop for the right reasons and in a way that was accessible to all. So with that in mind, it gives me great pleasure to introduce our guest speaker this evening. Professor Brian Davies is a fellow of both the Institution of Mechanical Engineers and the Royal Academy of Engineering, and has published over 250 papers on medical robotics. He is Emeritus Professor of Medical Robotics at Imperial College London, where he has been since 1984. He was the founder of the Mechatronics in Medicine section in the university, establishing the department as a centre of robotics surgery research, which developed the world's first clinical application of robots for prostate surgery in 1991. He founded the spin-off company Acrobot in 1999, which was successful in performing many unicondylar knee surgeries, which was sold on to Stanmore Implants worldwide in 2010. He's also the founder and managing director of, goodness me, that's very sensitive, that screen, of Signature Robots Ltd, a company concerned with minimally invasive, low-cost orthopedic surgery using small cooperative robots. The robot is currently being applied to minimally invasive unicondylar knee surgery, although it can also be applied to a range of small and low-cost surgeries as well, including trauma surgery. I know that Brian has had a close friendship for many years and has shared very much professional interest with Patrick in robotics and its application to surgery, as well as the profession and the education of engineers in medicine. So I am deeply honoured, Brian, that you would agree to give this evening's lecture. Brian, thank you very much, and we look forward to hearing what you have to say. Thank you.
Thank you very much for that kind introduction, and it's a great honour to give the talk today on cost-effective orthopaedic robot surgery. So I'll also talk about the early days of robotic surgery, examples of current systems that we have for robot surgery, both large and small robots. What do we mean by cost effective? And I'll then talk about some of my personal spin-off activities and augmented reality examples. Just to start off, this is something I was involved with as a manufacturing cell, but you can see that this sort of robot is not the sort of thing you'd want carrying out surgery, not a precise machine. So I started robotic surgery way back in 1988. I was contacted by a urologist surgeon, Mr. John Wickham, and he asked, was it possible to have a robot for prostate surgery? And I thought that was rather bizarre, but I agreed to do a laboratory study, and that led to clinical trials later on. My prostate surgery robot, Probot, I started out using a laboratory study. You can see in the middle here the Puma industrial robot, and we had to hang on to that an additional 3-axis framework to carry out the transurethral resection of the prostate. And I looked at that as a possibility, but then thought this is not really very safe to carry out surgery on people. And so we went on to look at a special purpose framework, and indeed we called it Probot, prostate robot, and had our first clinical trial in April 1991. Now, this was a very world first in using clinically a special purpose robot for surgery. So we went from that first research to clinical implementation in just 3 years. That would not be possible today because of all of the various requirements for regulatory affairs, particularly, and takes several years these days. And what we used there, you can see, is this small, see if I can get this. Yes, this is a relatively small framework with a standard urethroscope attached to it. So using the standard tools of the day into this framework, which was a means of constraining the cuts to a safe region. And once we'd positioned this robot in the right place, this arm at the back here was a gross positioning system, which we locked off for safety to ensure that we only moved within a small region with the active robot. Now, around the same time, in fact, a year later, the first clinical trials on a hip surgery robot, Robodog, were carried out, and this was using a 10-kilogram robot. And you can see here that the surgeon's been told that it's quite safe, it's been modified for safety, so seeing his head next to a 10-kilo robot is perhaps something he was very naive in his approach. But nevertheless, the hip surgery was used really to ream away the femoral canal, and in order to do that, at that stage, they had to lock down the whole leg with this massive framework you can see here, and that clamps the leg, and you're treating the whole thing as a CNC machining process, effectively. And subsequently, that has been used. The current version is called Think Surgical. Robodog was bought out by a Korean company, so nowadays it's a Korean Hyundai robot which is used quite naturally, and it's a very similar process to that previous Robodog version, an autonomous robot, and proceeding with again a similar clamping system. You can just see here much lighter clamps in place, but the whole thing is still a very large robot. More development has taken place on the pre-operative CT scans and so on, better planning, imaging and so on, but really it's a light leg clamp system that's being used. Now, many of you will have come across this intuitive surgical Da Vinci robot. This is actually used for soft tissue surgery and not for orthopedics. And you can see on the left here, the master controller, hang on, we'll go back, the master controller, and on the right, the slave. The slave system has got 3 tool arms and 1 camera-based arm. And really, the surgeon has got his head buried into this display using a 3D display. So he's not actually in charge of the patient. You have to have an assistant looking after the patient. And mostly this is being used for radical prostatectomy. So for cancer of the prostate, I'd say this is the machine that you should have, definitely. The results are so much better than open or even laparoscopic surgery these days. So very cost effective in spite of that $2 million capital cost of the machine, which is a pretty extraordinary statement. So what do we mean by cost effective? First of all, looking at effective. Well, the surgery's got to be at least as good as the conventional open or minimally invasive laparoscopic surgery, both in the short term and the long term. The problem is that the body is actually very forgiving. You can do a pretty poor surgical job, but then the body actually compensates, and in the long term, it's not that different from the high quality surgery. So we have to justify this in terms of effectiveness. And really it can take something like 5 to 10 years of follow-up studies for us to show the efficacy of the orthopedic procedure done robotically. So that's a pretty long process there. And then in addition, we can see the robot as being used for additional procedures just because you have got one, but often of marginal benefit. For example, that XI robot, the Da Vinci robot, can be used for various tasks which are really not very cost effective in their nature. So if you're looking at stones in the bladder, for example, which they recommend, it really isn't justified to do this. So we do have to look at recommendations for keeping the robot in use. So how costly is it? Well, it's not just the cost of that initial cost of the capital cost of the robot. The R&D itself can take several years, and that's not just to develop the robot and control system, but also to develop the 3D imaging, the planning and simulation, as well as the actual interventional control and safety implementation. And then regulatory affairs are now very complex and take a lot of time and money. So the CE approval for the system to show that it's safe in the OR, for instance, it doesn't interfere with the anesthetic system, and to ensure that the robot controller is immune to spikes of high energy from things like when you're heating the tissue, for example. We also require a process of in vitro trials, cadaver studies, animal studies perhaps, before we can get onto a small sample of patients to demonstrate the clinical effectiveness. The cost can also be an increase in complexity and time for the procedure. It's quite often the case, but at the end of the day, we get a better result. That structured workflow that you get from a robot, however, does help to simplify the process for trainees so they can come in and very quickly become proficient in a new procedure. Now, there are big and complex robots out there, such as this Mako Rio orthopedic robot, stands about 2 meters high, and this is typically used for unicondylar knees and joint replacement, and also hip surgery. And Mako sold this to Stryker in 2013 for about $1.65 billion. So it clearly is doing something, and it's nowadays a major player in the unicondylar knee replacement area, and is generally considered to be very cost effective. And you can see here the system being used in the OR. On this side, you've got the anaesthetist near the head of the patient, and then you've got the surgeons, the lead surgeon and assistant here operating the robot, which is all draped. And then in the back here, you've got similarly a couple of guys who are looking after the standard tools and presenting them to the lead surgeon. And they're all in these space masks, having an independent air supply because they don't want to be breathing bone dust from the patient. You can see here tracking system, light emitting diodes, which are attached to the tool and also to the patient. And this camera-based tracking system up here is looking at where is this tool in space, where is the body in space, and collaborating the two together. So the Mako Rio system has got a series of standard tools, which you can see here. In the middle is this rather large standard tool with this hemispherical burr on the end, which is used for machining away the cup, the acetabulum cup for the hip replacement. This has to be done right, otherwise you can end up with not enough bone left in the pelvis. So that's a rather large standard tool there. Here we've got a small burr which has a ball-ended cutter, and that's used to trim away the hip femoral canal, and also for use on a unicompartmental knee. Perhaps I should say at this stage that the unicondylar knees are much better than total knee replacement. If you've got a good cruciate ligament in place, then you can actually remove much less bone material. As a result of that, you can have a subsequent procedure when that joint wears out, the artificial joint wears out, and you can actually then use a total knee replacement for that subsequently. So it gives you plenty of bone material left for subsequent procedures. Now, here's a smaller robot assistive device. This is called the Navio Sculptor. You can see that here is the tool, which is tracked here by these light emitting diodes, and then the camera up here tracks where is that in three-dimensional space, and also where is the target, in this instance the bone, with another tracking system. On this here is a cutter, ball-ended cutter, which is cutting away within the go area, and when you're not allowed to cut, perhaps you might be saving the condyle of the ligaments of the knee, this tube here, the tube here moves down and covers the cutter so that you don't cut in that region. And this is as part of a system which is now here. Here is the display on a trolley, and this system was now owned by Smith & Nephew in 2015, and is used just for unicompartmental knees. And you can see here on the right the unicompartmental knee joint replacement, and you can see how much smaller it is than the total knee replacement on the left, particularly the femoral component, cobalt chrome material, very much larger than the uni system. So you can see that the uni would have much less bone removal than TKR. And here you can see the actual system with this guard that moves down over the cutter. You can see the tracking spheres for tracking where is the tool in space, and then this can be used to use the ball end cutter to remove material from the bone. But you can see that also these reflective markers here are actually tracking the bone position. And you're looking all the time at a display which is showing the amount of bone which has been removed, and eventually you want to get down to a green level where all of the material has been removed. So that takes a little while compared to using standard jigs and fixtures and oscillating saws to remove the material. So it is a bit more lengthy than the other system. You can see here it costs around 400,000, and it is considered fairly cost effective. It's a minimally invasive solution, which is a relative term. You can see here the incision is quite large, held open by retractors. Really, these days, we don't worry so much about having a small incision because infection rates have been shown to be almost the same, independent of the size of the incision. So it's a recent change in our thinking. Let me talk also about Omnibotics, which has been around for many years, a small robot that's actually mounted onto the bone of the knee. This is for total knee arthroplasty. And you can see here the actual device. This is a series of motors which are mounted directly onto the bone of the knee. And here we're holding a fixture which rotates through a series of angles to produce 5 separate angled cuts for a typical total knee replacement. So this has been around a long time, but it's been bought by Corin recently, a UK company from Bath in 2019. And this is probably one of the best aspects of that whole system, called the balance bot, because it's actually predicting what is the soft tissue balance so that the ligaments are not strained particularly badly. So we used to say it was all about the accuracy of our bone cuts that mattered, but now we're able to see that the body is a much more complex system than we previously thought, and things such as the soft tissue balance become even more important as we go forward with accurate cutting. Here's a simple small robot for spine surgery. This was produced in Tel Aviv by a company called Mazor for drilling into the spine pedicles to accurately put fixtures into the pedicles. We found previously that quite often the drill missed the pedicle and the insert was not actually anchored to anything. So it was a sort of get enough of them right, and it's a sort of average process. But here you can see a much better simple system for accurate screw fixation. Now, what you can see here is this round object, which is a T-bar onto which the robot here is mounted. And that's clipped as a T-bar support down to the onto the spine itself, and here onto the pedicle itself. And what you can see underneath that cover is this 6-axis small parallel robot with a series of motors at the top here. So it's a very small structure underneath that cover. Now that's been taken over as a company by a large company called Medtronic, and they instead have produced this quite large floor-mounted robot to do the same task. And they acquired Mazor for $1.6 billion just recently in 2018, primarily for the clinical data and not for the robot. So they're going to virtually dump the robot. So you can see here we've got rather a different trend. We've replaced a small, simple robot with a much larger robot, but this is flexible. It can be used for a lot of different tasks. So it's also used for abdominal surgery, for example. And in addition, I've worked with people in Taiwan, one of my former PhD students. They have another company called Point Robotics MedTech, and a similar process, but this time what they've done with this parallel robot here is to adjust the position of the drill so that it compensates in real time for the tremor of the surgeon or for the movement of the spine itself. So once you have actually got a location for where you want the drill to be, you can bring in this parallel robot and carry out very accurate surgery. So that's an in vitro test on a bacon back. Let me talk about my first spin-off company, the Acrobot Company Ltd. This was a hands-on or cooperative robot. Again, we ended up using this for unicondylar knee arthroplasty. This was Acrobot stands for active constraint robot, because we're actively constraining the surgeon to a safe region. So hence the term active constraint. So we started off with a small medium enterprise from just on robotic orthopedic surgery, spun off from Imperial College in 1999 after 8 years of preliminary research at Imperial College, and I founded this together with a colleague, Justin Cobb, a noted orthopedic surgeon. And we went on to do some very good clinical studies and eventually acquired by Stanmore Implants in late 2010. Now, what do we mean by active constraint control? You can see in the green area here, the safe area that you can move within. Typically, this is a tibial plateau, and you're machining that away. And then in the red is the forbidden area. You might damage ligaments and so on if you machine into that. So how do you move from one to the other? You can see that as we move out into this area, we gradually reduce the radial outward motion and move back into the center or side to side until eventually, if we get to the boundary, we can only move tangentially or directly back into the central safe region. So that's what we mean by active constraint. We had a pre-operative planner based on a three-dimensional CT scan of the leg to create a complete computer model of the knee. And you can see this here as a femur preoperative planner. You decide where it is that you want the prosthesis to be placed. You can choose different sizes, move them around, and position them, see how much bone is removed when you're using different sized prostheses. And then you can do the same thing for the tibia, moving the tibial tray around with the same activity, and then show the whole of the leg with the line of action between the center of the femur moving up to the center of the hip, and also the center of the tibia moving down to the center of the ankle. So those mechanical alignments are very critical as well in this process. Nowadays, you'd probably have a less busy screen than this with some artificial intelligence to determine what is the best particular prosthesis position and size, and suggest this to the surgeon for the surgeon's approval. I'd emphasize that this is using AI as a pre-operative planning process, not as the intraoperative activity. You never want the surgeon to say, I didn't know it could do that. That would be a disaster. So AI has its place, but is suggesting to the surgeon what is best rather than taking action independently. Now, the Acrobot we had applied here in vitro for, again, unicondylar knee replacement. And you can see here the system we used, which was quite a small system, again, located, sorry, this is an in-out motion and a pitch and a yaw, and that relatively small system is actually positioned by this gross positioning system, which is under the drapes here in grey. Once this is positioned in the right location, this gross positioner is locked off for safety, so you've only got the small motions of this system here. So this is really very much the same as my early prostate robot in concept of a gross positioning system. Now, going back early on, we had this system, which is from Patrick Finlay, Dr. Patrick Finlay, in his Armstrong project. So he supplied this green robot under contract, and you can see on the, this is quite cleverly done so that you can, okay, it's draped during the procedure, but then subsequently you can wash it down and you don't get any liquid going into the inside of the casing. And now this is a pretty robust structure because we're actually using this very large structure here for total knee replacement in our initial studies. That particular device is now actually in the Science Museum in South Kensington. So this is what we mean by unicondylar knee surgery. You can see how small this is with a relatively small incision for the joint being positioned with a tibial tray here and the plastic component here for low friction sliding for the femoral component here. We actually started with a small, excuse me, prospective randomized clinical trial with 15 patients, conventional, 15 robotic, and all of them had a pre-operative plan. And you can see here on the right, the robotic side, all of the what was planned is shown in white, what was achieved is in yellow, and you can see that all of these are very accurately located. Sorry, I'll get a bit of water if I may. Thank you. Thanks, Helen. So what we've achieved is in yellow and in white, And all of these robotic were within plus and minus 2 degrees of what was planned. Thank you. On the left, you can see the control group. And again, what was planned is in white, what was achieved in yellow. And this control group was really a series of surgeons who were very experienced in unicondylar knee replacement, doing the best that they could, but only 30% of them were within the plus and minus 2 degrees that we were aiming for. So without statistics, you can see how this particular system was demonstrated to be very useful. We used a slightly smaller system now. The Acrobot system was actually a trolley-based system with the active system pitch, yaw, and in-out mounted on it. And on the end, we had a two-axis passive structure for orientation of the cutter ball. You can see that here with the structure being held by the surgeon, and this here is a very small ball cutting the bone away to have problems here. I don't know why. It's better. I think we're okay now.
Okay.
So that doesn't seem right.
So, do you want to take a moment to get a drink?
Thank you.
Do you want to play that?
Sorry, hay fever season.
Is that okay?
Thank you. So here we can see how the orientation device is a passive orientation device, and the center of the ball cutter here passes through an axis here, here, and here. And if you think about the way in which this is rotated around, you're not actually moving the center of that ball. That is purely located by the powered system. So this passive orientation device is very useful. Now this should start automatically, but it doesn't. Let's try that. Okay, forget it. So this particular device moves in and out and in pitch and yaw, and then on the end we've got this orientation device which should have automatically run, but it's not. Any suggestions?
Yeah, it's yeah, there isn't the media's not showing up, so it's not going to play, I'm afraid.
Isn't it? Oh, right. Okay. Well, the idea was that you could see how orientating this around would have given you the required change of orientation around the center of this ball cutter here. And here we've got the sculptor actually being used on a knee, patient's knee, and you can see the cutter is going down inside the knee here. And whilst we're doing that, we're displaying here what you can see down inside the dark hole. So you need that display to be seen at the same time. All of the structure itself is draped apart from the actual cutter, which is sterilized. And again, we're tracking the position of the bones themselves using this, in this instance, an arm, which is purely measuring position. Our subsequent history of the Acrobot was that we had excellent surgical results, and the venture capitalists sold the Acrobot to Stanmore Implants worldwide in 2010 with no benefit to the founders. And I say this as an example that if you've got a small company spin-off, you really want to try and ensure that the venture capitalists have less than 50% of equity, because otherwise they can turn around and say, no, we want to sell the company. You, I'm sorry to say, are Class B shares. We've got Class A shares, only have money for Class A shares, and you've got no say. So really important point to keep control of your company. Another point was that along comes SIW, the Stanmore Implants worldwide, had set up an American office, and we're going into the States, and they announced this, and then the next month along comes Mako and says, no, we're suing you in 3 states for infringement of our patents. Now, we knew that they copied our patents, but that was something that, yeah, we could countersue. They, Stanmore Implants, could countersue and probably win. But 2 days later, the Stanmore Implants board said, well, we might not actually get costs for this whole procedure. So we're talking about $5 million here. And so they said, we'll give everything to Mako and give in. And the point I'm making here is that it's not about the strength of your patents. It's really about how deep are your pockets. So you've got somebody like Intuitive, had a court case with Computer Motion way back, and Intuitive won simply because they had much deeper pockets than Computer Motion. So Computer Motion have disappeared totally and were forbidden to work in this area at all subsequently. So it's a very difficult area, the whole of robotic surgery, for this litigation reason, and we're really trying to ensure that it doesn't happen. It would be nice if we could do that in the UK, if nowhere else. Now, I also looked at some additional aspects for augmented reality display and artificial intelligence. And here you can see Smith & Nephew research, one of my colleagues, using here the head-up display in blue to paint away the bone on the actual artificial ligament leg. And here you can also see a patella being placed in an accurate location, and there you see it on the actual cadaver in the right location. And then finally, we've got some bone cutting going on here with the display, augmented reality display, showing the actual position of the cuts on the bone as an overlay. I'd like to finally talk about the Signature Robot Ltd, which is a company I recently spun off and I've patented. And this has got a lot of potential applications for joint replacement, small joints, but we're particularly trying on unicondylar knee replacement. It's a hands-on robot, just a cooperative robot, just like Acrobot and Mako, but low cost and small. And the cutter is held between the thumb and forefinger with the wrist supported onto the robot. And it's quite clear that the surgeon is therefore in charge. On the left, you can see the digital twin of the robot, the actual robot on the right, as we're moving it around in pitch, yaw, and in out motion. and you can see the vectors on the left digital twin. And in addition, we can drill down a hole, and you can see again on the digital twin what it looks like when we go outside of the green area, and you get vectors showing you the forces that are moving you back to the center. In addition to that digital twin, you do get forces actually fed back to your fingers to show you that you've moved outside of the region. So it's constraining you back again into that central region. And then in addition, we've got this area of a hemisphere, which is typical of femoral knee implants that's required. And you're moving that around again with this display coming back into showing you the forces that are being exerted and which direction you have to move in order to avoid cutting outside of the boundary. So this is the sort of system we have, and this time, whoops, we have put a passive arm in here, mounted on the side of the operating table, and the actual robot itself is here, and we're actually supporting where you're putting your hand on this passive arm. And the idea is that if you want to work on the femur, for example, up here, then you can move into that location. Then if you want to work on the tibia, you just unlock the passive arm, move down, and you can move within that local region as well. So it's quite a good implementation to allow easy access to the whole knee. We've also got a patent on surface imaging, looking at trying to differentiate between tissue types, bone, muscle, fat, and skin, using a laser and a camera to look at the tissue itself. And you can see here the spot of the laser on the cadaver specimen. But the idea here is purely that we're using a speckle pattern broadcast onto the surface of the material, and using this speckle and artificial intelligence, we can actually detect where is the skin, the muscle, the bone, and metal retractors in this instance. So here are all of the skin, muscle, and bone, and you can more or less see this on the left diagram, but you could not see this with the eye in that particular system on the right. So the AI is pretty useful in detecting this. Now, as I say, we've got a patent on that, and so far it shows that with this speckled concept, it's a potential for real-time use and really excellent classification accuracy and good at differentiating tissues. So it's very useful also for soft tissue as well as orthopedics. So we have great hopes for that in the future. So to conclude, overall, you can see orthopedic robotic surgery is a very crowded area. It's developing very rapidly, particularly when it is shown to be cost effective. And there are quite a lot of solutions around, I'm afraid, which are not cost effectively. So we see two contrary trends, really. This larger, expensive robots that can carry out a whole range of procedures, and then smaller, simpler robots restricted to a few procedures. And I think that we'll probably see room for both in the future. Thank you very much.
Thank you very much, Brian. Sorry you're suffering with all of that tree pollen that's coming out of St James's Park at the moment. I believe that we've got some questions I'm going to. She can help me with that. First of all, thank you ever so much. I'm what you said right at the very end about the two very distinctive pathways that are developing with these robots. What do you hope we will see in the coming years as those two things kind of diverge?
Well, I hope that we'll see many more smaller, simpler devices. The idea of the signature robot is that you could have one in every operating room rather than for large systems, one in every teaching hospital, for example. So as a result of that, I think that we will be able to get high quality robotic surgery readily available in every OR. The other larger systems will tend to be more difficult, I think, in future to justify. They will be used really for quite a range of different procedures, and there you're actually relying upon a very thorough pre-operative planning system, simulation system, imaging system to go with that robot and the way in which it's structured. So I think they're very different processes, but we'll see both. Each has its place, I think.
Yeah. So do you expect I mean, I know you've been very much involved in developing mechatronics programs at the university and so on. Do you think we're going to see a new stream of engineers who are particularly focused on delivering surgery and being in the surgical environment themselves, you know, developing those clinical skills to be in that environment? Or do you think it will still stay very much, you know, in the engineering kind of community?
I think we must have better cooperative work with surgeons. There's no point in coming up with bright ideas that nobody in the surgical world is interested in. So I think you've got to continually collaborate with surgeons, and I think, and I hope we will see closer and closer collaboration between engineers and surgeons in that area.
Yeah, I would agree with you. Certainly, it does seem to be the way that that things are going now. That we're becoming just as much doctors as engineers, I think, in certain aspects. I would very much like to open up questions to our guests here, and also anyone who is online who would like to ask any questions of Brian. Please feel free to add those to the chat, and I can see the chat here. So if you would like to ask any questions, so over to the floor. They're all very quiet, Brian.
Pattern challenge. Do you see the same challenge in the European context as in the US context, as you mentioned? And what solutions are there? Because it seems like it's an open secret, this power dynamics at play, but what does the solution look like?
I think that certainly the experience we've had is that the states is the particular ones who are doing all this litigation, particularly prone to it. But talking to, for example, CMR, who are doing robots in the UK in Cambridge, particularly a robot which is virtually taking on the Vinci robot for soft tissue directly, and they expect to be sued and really have taken great efforts to ensure that their financiers are quite happy for them to counter-sue. And I think that's necessary. In other words, you've got to have somebody with deeper pockets who are prepared to counter-sue and take this on. In Europe, we don't see the same sort of problems. So hopefully we will avoid that going forward. it is not a good trend. Yeah.
We're getting one or two questions online. I've seen a question from John Lowe here, and I'm going to come back to that, John, if you don't mind. I just wanted to jump to John Wood's question because it fits with what we've just been talking about. Do you see robots at some point in the future replacing surgeons completely?
No. I'm not one who likes to think of autonomous robot systems. I know that the Robodog and Thin Surgical are continued with that autonomous line, but even after this time, 20 odd years more, it has not really taken off. So I think that the surgeons really want this synergy between themselves and the robot, and this whole concept of what we call cooperative robots. I think it is something we will see more and more. So the surgeon is trained to take responsibility for his patient. So putting it in the hands of a robot, it goes against the training. Now, you can get small aspects of the whole thing, which will be autonomous. You can stitch very readily, automatically, for example, in soft tissue surgery. There's no reason why you wouldn't have that as a small autonomous activity within the total. But the total activity, I think, has got to continue to be within the hands of the surgeon. Some people say, oh, well, that's only a short-term trend, but I don't see it happening in the next 20 years anyway. Yeah,
and I think that it's human nature as well, isn't it, Brian, that people want to have human contact as well to the person that's actually going to do the operation. So I don't think we're ever going to see that point of. I'm going to come back to John Lowe's question now online. He wanted to know, are there enough engineers coming forward into biomedical engineering, into this particular field? And he's particularly thinking about the promotion of STEM to young people. Do you think this is a great opportunity, this kind of technology, to really inspire young people to come into the profession?
I think it does, and we're fortunately seeing quite a number of girls coming into this area because they do like the whole concept of medical engineering as such. So I think it does have a good future, but we do need to encourage people to take that sort of application-oriented route if we're going to see the benefits in surgery. Personally, I think we've developed far too many erudite papers which never get translated into application areas. I'm a bit of a Philistine in this area, as an academic, I'm sorry. But I do think that we need to apply what we're doing much more. That would be a great benefit for us.
Yeah, absolutely, and would give a lot of people interest and enthusiasm, I think, to take on a career in biomedical engineering, most definitely. I'm kind of Alan. Let's go to you.
Can I ask you a question, Brian, about robotics in other fields of medicine? Is there cross-fertilisation going on, or are there pockets of people working in particular areas, working in isolation?
They do tend to be so different that there's not that much cross-fertilisation. I mean, if we're talking about robots in the home, robots for disabled people, etc. I've worked in that area as well. They do tend to be rather distinct. Clearly, a lot of the programming and so on, and the planning and simulation of what's taking place has a crossover, but they're so different. If you talk about particularly the hands-on collaborative, cooperative robot. Collaborative robots, you can sit one alongside somebody on a workbench, and you have a person being replaced by a robot, and the robot doesn't damage the person alongside them. That's the way collaborative robots are being. more or less defined these days. So cooperative is I think, the way for surgery.
Thanks for that. Thanks for that question, Alan. We've got a question from Ian Josbury. Given the cost of approval these days, is it now an environment for only the big companies, or is there still a place for small innovators, do you think?
Certainly the small innovators for coming up with new ideas and starting the process. I think that eventually you do need to get on board with somebody who's going to do all of the additional aspects. For example, in my instance, we've concentrated on the robot itself and much less on the standard aspects of the imaging, planning, simulation processes, which really are fairly bread and butter to a fairly large organisation. So I think you can go so far, but then after a while, it's probably best to have collaboration with a reasonable sized company, in particular because it is going to take a little while to get those regulatory approvals through, and you do need that cash flow during that process. So there is a tendency to lead, in my view, into something that is fairly well funded.
Yeah.
CMR, for example, Cambridge Medical Robotics, as their work, is rather unusual in that they managed to get a lot of Italian money into that with high net worth individuals, sufficiently large that they were able to develop a system themselves without having to then go to yet another even larger organisation. So there are different trends, but I think the majority would see the need to merge with a relatively large organisation.
Yeah.
Take them forward.
Yeah, thank you. And one final question before we finish. What percentage of partial knee replacements are currently using robots? Is this now common, or are there still some? Is there still some way to go before it's a commonplace thing?
If we talk about unicondylar knee replacement, which, as I've said, is very bone sparing and desirable, looking at them really done by hand, you could see with our control study how difficult it is. And the results from some of the early joint studies showed quite poor results manually on using unicondylar knee replacement. It looked very easy in the early days because people from Oxford Knee Orthopaedics really expert in this, and they did a tremendous job. And so a lot of newcomers jumped on the bandwagon, and then we ended up with very bad results in the joint registry.
Right.
So that's the area where you can see that the robot itself, such as the Mako system, really is of great benefit. So yes, it's got a big price tag to start with, but really the results, I think, are consistent, and they get a very good result. So I say again that it is, in spite of the cost and the size of the robot, cost effective.
Well, thank you again, Brian. Thank you very much for both your presentation and for answering many of these questions. I'd like to take this opportunity to thank you and give you a quick round of applause before I invite. I'd like to now call on Professor Anthony Bull to give our closing statement. Thank you.
Well, that was fantastic. I really enjoyed that, Brian. So, Chair, ladies and gentlemen, medical, biomedical, mechanical, bioengineers, I don't know what we call ourselves, but I would call myself all of those or none. Yeah, I think we should all thank Brian for his fantastic lecture and for his work in medical robotics and for delivering this lecture to us today. I just want to highlight some key points that came out that I thought were interesting to me. So first of all, I think Patrick himself would have liked this lecture. There are a few things that were mentioned here that I'd like to pick out. So one of them is that this is all very difficult things you're talking about. It's really, really hard. It's all about good ideas, very good ideas, smart design, and cost effectiveness. And that is underpinned by all this doggedness and hard work and focusing on detail, and the detail is really important. I remember some of the things that we worked on and that Patrick was very keen on in this division ages ago. One of the things that he was a champion of, we've already heard, in collaborating between institutions, the IET or the IEEE, I can't remember what they were called at the time, getting us to work together on particularly a series of meetings on appropriate healthcare technologies, cost effectiveness. He was very passionate about this. And it's something that actually personally, changed quite a lot of my own personal research career, and I have a substantial activity in that area because of the kind of encouragement of Patrick. That's something I'll carry with me now forever. I think there's also the kind of determination and doggedness that Brian has shown here, that Patrick showed in trying to morph this group into something that represented these medical engineers, biomedical engineers, bioengineers through many name changes. So we had many fights with, I remember sitting in the chief executive's office here in this building and having the most awful meetings. And Patrick being, it's a former chief executive, so I feel I can say it in this lovely building. And Patrick, just persisting and continuing and actually sort of mentoring me gently, not to blow my fuse. What's interesting, I think, is that there's a lot of kind of history here and secularity. I mean, Brian started his robots in 1988. I came to Imperial in 1989, and eventually I came to this building, this institution, because Brian said, you need to come along here and get involved. And that's where I met Patrick and others. And actually, whenever anybody thinks about their professional interactions with Patrick, it's actually synonymous with the work here. And it wasn't about him, it was very much about the work and doing good things. And I think that's wonderful. I think the good things he did, he stepped in when we were running out of sponsors for prizes for this day that we've had today. Ferdinando, who was named on one of your slides, who leads the Hamlin Centre now at Imperial College, was the inaugural winner of the PhD prize on this day many years ago. And so, yeah, today's a very special day because you, Brian, could give this lecture, your fantastic lecture, a very special day in the context of the naming of this lecture, and our friend and colleague who we remember today, who's given much to this field, much to this institution, to medical engineering more generally, and someone who I've been proud, and many of us have been proud to call our friend and colleague for many years. And so I invite us to give thanks to Brian, and we will share a drink afterwards.
Thank you, everyone, and thanks to everyone for joining us online. We really appreciate it. If you want to get involved with the biomedical engineering division here at the institution, please get in touch. We are a very welcoming group and we'd love to have you join us. So thank you very much. Thank you.